next talk is given by Christian Koester, and so it's Control L.
So I'm going to talk about joint work with James Lee. And so we were not quite sure if this is a good title because there's a lot of long words and it's a bit cumbersome to say. So an alternative title with shorter words could have been this. But maybe not everyone knows what these abbreviations stand for. So here's another suggestion, how to measure uncertainty in a metric space. And I'm going to explain what this means. So MTS, metrical task systems, is the following problem. We are given a metric space, and our algorithm starts at some point of this metric space. And then at each time t, first a cost function is revealed that assigns to each point of the metric space a non-negative cost. Then the algorithm selects a point in this metric space, and the algorithm pays the service cost at this selected point, and also pays a movement cost, which is the distance from the previous point to the current point. And then we measure the quality of such an algorithm by its competitive ratio. So we say an algorithm is row competitive if the cost is at most row times the optimal cost. Or in this setting, we can say something more refined. So we can say the algorithm is alpha beta competitive if the service cost is at most alpha times the total optimal cost, and the movement cost is at most beta times the total optimal cost. And yeah, so this is a very general problem in online algorithms, generalizes, for example, also the K-server problem. In contrast to problems from earlier talks today, the cost function is revealed before we choose the new point. And we compare ourselves to an optimal algorithm which can also move around in the space, and that's why we cannot expect to have a regret bound, but have this multiplicative competitive ratio instead. Let me also mention what HSTs are. So HSTs are special metric spaces which are similar in some sense to every other metric space. So it's a tree where the length of the edges decrease geometrically down on every path from the root to the leaves. And the importance of these spaces is that every metric space can be embedded into a random distribution of such HSTs, or more precisely into the leaf space of these HSTs. So the actual metric space are just the leaves. And therefore, if we have an algorithm for HSTs, we have also an algorithm for general spaces, which has the same competitive ratio up to the log n factor. And what has been known about MTS on HSTs is that, and due to a very recent result, that we can be simultaneously log n competitive in both service and movement cost, or we can also be 1 competitive in service cost and log square n competitive in movement costs. And what our result is that we can unify those two bounds, so we can be 1 competitive in service cost and log n competitive in movement costs on HSTs, so this is tied. And on general metric spaces, we then receive bounds of 1 and log square n, which is not tied, probably. But what I think is more interesting than the result is the techniques that we used. So we are talking about randomized algorithms. So therefore, the state is not just one leaf, but it's a random distribution of leaves. And we can therefore describe the state by a point in this polytope. So xu is denoting the probability that our algorithm is in the subtree rooted at u. So the probability of being in the subtree rooted at the root is 1. And the probability of being in the subtree rooted at u is equal to the sum of these values for the children of u. And then we can just run mirror descent in this polytope. So when the cost function ct arrives, we move to a point which minimizes the sum of these two values. So the first inner product of x and c is just the expected service cost at this point, ct, if we are at point xt. And the second term is the Bregman divergence of the new point and the old point. So the second term ensures that we don't move too far away from our old point, because we have also the movement cost to pay for, of course. So the only thing one has to choose now is what do we choose as the function phi. And the function that achieved the 1 and log square n regret bound in the recent paper by Bubeck, Cohen, Lee, and Lee is this function. So if we ignore the eta and delta for now, then this looks essentially like an entropy. So we have additionally weights here because the value of the uncertainty at higher scales is larger than at lower scales. However, so our point is just our state is just a random distribution over the leaves. So the true entropy should only include the leaves in the sum and not every internal vertex as well. But with this term, we don't know how to put the weights in there, so we can rewrite this as a conditional entropy. And then the regularizer that we used is essentially this term when we add back in the deltas and the weights and etas. So this is the regularizer that gives us then the guarantee of 1 competitive service cost and log n competitive movement cost. So this algorithm also has a nice interpretation in continuous time. So the evolution of so this fraction xu over xpu is the probability of being in the subtree rooted at u, conditioned on being in the subtree rooted at pu. This evolves according to this formula. So here the lambda pu and alpha u are just Lagrange multipliers which ensure that we remain in the convex body K. And this cu hat is this term, so xl over xu is the probability of being at L conditioned on being in the subtree of U. If we multiply this by CL, then it's the expected cost at L conditioned on being in the subtree, summing over all L. This is just the expected cost conditioned on being in the subtree of U. So this is the force that drives the motion of these conditional probabilities. And we see now also why we have this delta here. So without the delta, it would just be multiplicative weights, multiplicative update algorithm. But the reason why we need the delta is that otherwise the algorithm would move too slowly when these conditional probabilities come close to 0. So delta ensures that we still have some mobility. And yeah, so let me briefly talk about the analysis. So the analysis of the service cost uses as potential the Bregman divergence. This is relatively simple. The movement cost analysis is the actually tricky part here. I probably don't have time to go into this now, but we can talk about this at the poster session. Let me just briefly mention the main open problems here. So one is, can we do something similar on general metric spaces so that we get tight bounds on general metric spaces, and can we extend it to the K-server problem? Because for K-server, the known bound on HSTs is log square K, achieved by essentially the analog of what achieved log square n for metrical task systems. So doing the same kind of modification for K-server could hopefully give tight bounds for K-server on HSTs. Thank you. It's a discrete metric space with a finite number of points. Because on an infinite metric space, there's no competitive algorithm. So the service cost is alpha competitive against the total offline cost, because the offline algorithm could always just not move otherwise, then it would have movement 0. So we have to compare it to the total offline cost. Yeah, so one can discretize it, and we also wrote it down in a discretized way. But I'm not sure about the runtime.